All right, let's take another question. The next question is, why is quantum field theory difficult and how to learn it efficiently? Well, this is not a question about physics. Well, it is about physics, it's about quantum field theory, but it's not a technical question. Let's put it this way. Why is quantum field theory difficult and how can we learn it in a more efficient way? This is the question. Two questions, actually. But let me add another question to this, make it three. Um, because first of all, we have to decide on this. Is quantum field theory difficult or not? Some people would say, some physicists would say, no, it's not difficult, and some would say, well, yes, it is. In my opinion, it's difficult. It's a difficult subject in theoretical physics, but um, we have to kind of, look at this question or problem in a more scientific way. As a physicist, you have to think about this, right? Is quantum field theory difficult? How you decide about this? Well, how we can basically define the difficulty of a subject. How we know that general relativity, for example, is more difficult than special relativity. I think there are parameters, there are criteria that can tell us if a subject is difficult or not. Okay. Again, this is not physics. This is kind of philosophy, but you can put it the same way we try to solve problems in physics. One parameter, one criterion to decide if a subject is difficult or not, in my opinion, is the time it takes to get the background required to learn that subject. For example, what kind of background you need in order to learn about special relativity? Well, you have to know something about classical mechanics, Newton's laws of motion, electromagnetism, Maxwell's equations, at some level, and then it would suffice. I mean, and simple calculus, more or less, would suffice. I mean, it's the enough background to learn special relativity. Okay, but in order to learn general relativity, well, you have to know about tensors, of the differential geometry. You have to know about special relativity. So the volume of information, knowledge you need to learn general relativity is much more than what you need to learn special relativity. So this is one parameter, one criterion that shows that general relativity is more difficult than special relativity, as an example. The other parameter or criterion is the time it takes to do a typical calculation in that subject. For example, a typical calculation in general relativity, for example, calculating the angle that a light ray would bend from straight line when passing nearby the sun, for example. This is a problem, a famous problem that Einstein solved as an example of the application of general relativity in the early 20th century. It's a long calculation, okay, compared with what you typically would encounter in special relativity. So this is another criterion telling you that general relativity is more difficult than special relativity. And another criterion, more importantly, and this is very connected to the question about quantum field theory, is the number of concepts and ideas floating around when you basically attempt or try to learn a concept in that subject. For example, when you try to understand Einstein field equations in general relativity, you have to take care of different signs. You're working with tensors, summation, of all these indices, etc. You're working with partial differential equations, which are kind of coupled all the time. The metric, the sign of the metric you choose, different notations, etc. You have to keep track of all these to do a single calculation or to understand what's going on. Now, as the number of these concepts, floating concepts, is increased, it gets more difficult to keep track of all these details and do whatever you're trying to do. Now, in quantum field theory, the main problem with quantum field theory. The main reason that makes quantum field theory more difficult is this criterion, in my opinion. Because even in a very simple setting, for example, in trying to quantize the Klein-Gordon field, this is the beginning of quantum field theory. You have to worry about so many details. You have to know some background, what's Klein-Gordon equation, why instead of interpreting the solution as a wave function, we interpret it as a field, etc. You have to keep track of different signs. Why the sign of the frequency or energy term in the Fourier transform of the field, the Klein-Gordon field, should be negative. So you have to keep track of all these signs. And then you have to know about, this is a very simple example, but it tells you what's going on, what I mean, basically. You have to, consider the difference between Lagrangian and Lagrangian density, for example. These are all very simple details, extremely simple, right? However, you have to keep track of all of them at once as you try to do a single simple calculation. So the main reason that I think that quantum field theory is difficult is because of a large number of these concepts and details floating around when you try to solve a problem or learn something in quantum field theory. This is not the case even in general relativity. In general relativity, well, equations are difficult. For example, Einstein's field equations, they're coupled partial differential equations, as I mentioned earlier. But still, the number of details you have to remember at each step is not that high, it's not that large. But in quantum field theory, you have to worry about all these details. On the other hand, one more thing that makes this more difficult, is that there are equivalent but completely different formulations of the problem. For example, we've talked about canonical formalism, and we're going to talk about path integrals next time. But if you look at these as a beginner, you'll see that, well, there is no connection between these two, path integral formulation and canonical formalism of quantum field theory. What's the relation between these two? Well, they are related, they are equivalent actually, but they look very different. I mean, mathematically, they are completely different. So it's another reason that makes quantum field theory a difficult subject to learn. However, I should add that conceptually, quantum field theory is not difficult to understand and to learn. In fact, if you have learned non-relativistic ordinary quantum mechanics, then there is no, obstacle. There is no reason that you shouldn't be able to learn a quantum field theory. But it takes more time, and you have to find the right textbook, etc. So we talked about different books and the problem with most of these, but finding the right material, textbook, etc., is another problem. But anyway, I guess this is the reason that quantum field theory is difficult. But how to learn it efficiently? Well, my strategy has been in teaching and also when I was a student and learning quantum field theory to begin with a big picture, which is by definition a rough picture. I repeat this in all my lectures. And don't worry about details, don't pay enough attention to, small details, although they are important, but you can ignore them. And look at the big picture, understand what's going on. When we say quantizing the Dirac's field, what we mean by quantization procedure. What's the Dirac field? What's the difference between the Dirac field and the Dirac wave function, for example? Understand this big picture, and then get back and read and go to lectures, whatever, and try to add more details to this picture in your mind in order to refine it. And after a couple of repetitions, you're going to understand fully what's going on. Technically, you're going to understand all details about calculations, etc. So this is the reason that when I teach quantum field theory, I start with a very rough picture. I mean, giving examples of from classical physics. You have a swimming pool, you have waves. Waves represent particles. Then, in order to create a particle, you drop a pebble, for example, excite the surface of water, and that excitation resembles a simple harmonic oscillator. So, simple harmonic oscillator can be understood using relativistic ordinary quantum mechanics. So, this is the way we treat a field, a quantum field in quantum field theory, so on and so forth. So, by these examples and understanding the big picture, you're not going to be able to do a calculation in quantum field theory, but as you go ahead and you repeat this and add more details, after 3 or 4 repetitions, you're going to have enough material to understand what's going on in a standard textbook on quantum field theory. In fact, I think this is the way we humans learn about the world, not only in science and physics. We learn about the world around us as a kid, for example, this way. If a say 4-year-old kid asks you about an ATM machine, say, okay, how does an ATM machine work? How you get money from an ATM machine? You're not going to tell all these details about the connection between different banks. You have a job. Some people pay you, and they put that money into a bank. This ATM machine is connected to that bank. There is some fee when you try to get money. No. You forget about all these details, and you tell that kid that, well, this is a machine. There is some money inside, and when you put your card, there, then you can get money and you can decide how much money you need. This is the simple big picture that you have to provide that kid. And as they grow up, they're going to add more details to this. They're going to refine their picture of the world around them. And this way, we grow up, all of us. This way we learn about the world, and this way we can learn about science and quantum field theory. So in quantum field theory as well, and string theory especially, this way. You start with the big picture, forget about details, and then repeat by adding more details.